Hello and welcome to this video on advanced trigonometric calculus. The original purpose of this video was a sort of introduction to the type of calculus you need for polar coordinates, lots of sines and coses, and it's just looking at the material we've already met in the standard A level. So to start off with, we're looking at the intervals of sine 2 theta and cos 2 theta. Now you should already be aware that if you differentiate sine you get cos, differentiate cos you get negative sine, differentiate negative sine you get negative cos, and then back to sine. So this circle here is showing you how you differentiate and go around in the cycle. Okay, and if you want to integrate, then you can go anti-clockwise instead. So the integral of sine is negative cos. But as well as that, if we've got 2 theta there, if we were applying the substitution method, the opposite of the chain rule, then the integral is going to be negative a half cos 2 theta plus c. So the sine is giving you negative cos, but you're also having to divide by the 2. And of course we need to write plus c on the end because this is an indefinite integral. I'm not going to be writing plus c throughout the video, okay, but just on this first slide, just a reminder that we should be doing that. The integral of cos 2 theta, again, we can go anti-clockwise around the circle. The integral of cos is sine, but we also need to halve that as well because of the 2 theta there. So those should be fairly standard. Moving on, we need to be aware of identities for sine 2 theta and cos 2 theta. Now for sine 2 theta, it's basically 2 sine theta cos theta. There's only one version of that. For cos 2 theta, there are 3 ways of writing it. And for our calculus, we need to use the ones which are exclusively in cos squared and sine squared. So one of those, the one in terms of cos squared, is 2 cos squared theta minus 1. And the one in terms of sine squared is 1 minus 2 sine squared theta. And again, you should be aware of these identities already from the A-level trigonometry. So if you want to integrate something like sine theta cos theta, hopefully you recognise that as being part of the double angle formula for sine. Okay, so we can rewrite the integral of sine theta cos theta d theta as half of the integral of sine 2 theta d theta, because sine 2 theta is 2 sine theta cos theta. And now we're just doing what we did before when we're integrating sine. The integral of sine is negative cos. We have to divide by 2 again, so we're actually going to get a negative 1/4 cos 2 theta plus c. If we want to have 3 theta or 5 theta or k theta, for example, we can rewrite sine 3 theta cos 3 theta as half of sine 6 theta. So whatever the number of thetas is, like sine 2a, we've got the sine 2a is 2 sine a cos a. So sine 6 theta is 2 sine 3 theta cos 3 theta. So if we've got sine 3 theta cos 3 theta, that's the same as half sine 6 theta. And then when we integrate that, the integral of sine gives us a negative cos, but we need to divide by 6. So the answer is negative 12 cos 6 theta. For the next one, sine 5 theta cos 5 theta, that's going to be the same as half of sine 10 theta. And again, when we integrate that, the integral of sine is negative cos, and we need to divide this time by 10. So we get negative 1/20 of cos 10 theta. And then in general, if we have sine k theta, cos k theta, and notice those numbers, whatever they are in front of the thetas, have to be the same for this method, because sine 2a is 2 sine a cos a, where the a's are the same as each other. So here, again, we're going to double the number of k thetas, just like we doubled the 3 theta and the 5 theta above. Sine k theta cos k theta is the same as half of sine 2k theta. Again, when we integrate that, we're going to get a negative cos, but we need to divide by 2k this time to get a general formula of negative 1 over 4k cos 2k theta. And if you look at the 2 previous examples, you can see that the denominator of the fraction is indeed 4 times bigger than the number of thetas in the original integral. So that's why there's a 4k on the denominator. Something else you need to do at A level is to integrate sine squared and cos squared. So in order to integrate sine squared theta, we start with the double angle formula for cos, which is cos 2 theta is the same as 1 minus 2 sine squared theta. We make sine squared theta the subject of that, so we could add 2 sine squared theta to both sides, take away the cos 2 theta and divide by 2. And once you've got sine squared theta written like that, you can then integrate it. So the integral of sine squared theta d theta, the integral of half is a half of theta. The integral of cos 2 theta is going to be sine 2 theta. The minus sign isn't going to change, but we are going to divide by 2. So we get a half theta minus 1/4 of sine 2 theta. And then similarly for cos squared theta d theta, we start with the double angle formula for cos, which is cos 2 theta is 2 cos squared theta minus 1. we make cos squared theta the subject, and the only difference, as you may notice, between the expression for sine squared and cos squared is that there's a plus rather than a minus. So then when we integrate that, the only difference in the answer is that it's a half theta plus 1/4 sine 2 theta. So now we're going to look at what happens if we want to integrate sine squared 3 theta, or indeed sine squared k theta, so there's more than one theta. So we start off by using our integration by substitution method, again from A-level maths. So we can let u equals 3 theta. We also need to get rid of the d theta. So we do du by d theta equals 3, and then we rearrange that to make d theta the subject, so 1/3 du. And then we can do our substitutions. So we get the integral of sine squared u, but we are timesing that by 1/3 du. The third can come out the front as a multiplier. And again, we're integrating sine squared u du, just like we integrated sine squared theta d theta before. So that gives us 1/3 of half of u minus 1/4 sine 2u. And if we just expand the brackets, we get 1/6 of u minus 1/12 of sine 2u. But then we replace the u with 3 theta. So we get 1/6 of 3 theta minus 1/12 of sine 2 lots of 3 theta, which is a half theta minus 1/12 sine 6 theta. And notice that we've still got that half theta. That was a half theta when we just had sine squared theta to integrate before. That hasn't actually changed. What has changed, however, is that we've now got 6 theta rather than 3 theta, and we're dividing by 12 rather than dividing by 4, which we had for the simple sine squared theta. So in general, okay, and we could do this as a full method, but the formula we would get, the integral of sine squared k theta d theta will be a half theta. That will always be the case, minus 1/4k, so timesing the denominator by k. So where we had 3, we get 12. If we had a different number, we would have 4k. Where we had sine squared theta, we just got 1 theta there, so we just have a 4 in the denominator. Sine 2k theta, and again, the k theta has been doubled there in the sine term, just like when we had sine squared 3 theta, we had a sine 6 theta term in the answer. Integrating cos squared k theta d theta is very similar to integrating sine squared k theta d theta. So without going through the process, the only difference is going to be that, again, there's going to be a plus rather than a minus. So when we integrated cos squared rather than sine squared theta, we had a plus rather than a minus. This is going to be the same as sine squared k theta, except with a plus there instead of the minus sign. If we have an expansion like sine theta plus 3 cos theta squared to before, then again, the first thing we would do is to actually expand it. So we get sine squared theta, we get sine theta times 3 cos theta but doubled, which is 6 sine theta cos theta, and then 9 cos squared theta. And we need to integrate each of those terms individually. Now we've already seen how to integrate each of those terms one by one, and now we're just doing all of them in one go. So before we integrate it, let's rewrite 6 sine theta cos theta as sine 2 theta, the same way that we did that when we were integrating sine theta cos theta, or sine 2 theta cos 2 theta, whatever we may have. Okay, so when we integrate this, the integral of sine squared theta is a half theta minus 1/4 sine 2 theta. The integral of 3 sine 2 theta, well, the integral of sine is negative cos, but again we have to divide by 2 because of the 2 theta. So that's negative 3/2 cos 2 theta. And then to integrate 9 cos squared theta, well, I've integrated cos squared theta and I've multiplied it by 9. And of course, if you wanted to, you could expand the brackets and you could collect the thetas together and the sine 2 thetas, and there'd only be 3 terms plus the c in your final answer. This may seem a bit pointless, having just done the one with a 3 in it, but there is a reason for me picking this. So if we integrate cos theta plus sine theta all squareds, again, first thing we want to do is to expand the brackets, which gives us sine squared theta plus 2 sine theta cos squared theta. You wouldn't necessarily write them in that order, but I've just put them in the same order as they were in the previous example. The integral of 2 sine theta cos theta is the same as sine 2 theta, and then we can integrate each of those terms individually. So the integral of sine squared is our half theta minus 1/4 sine 2 theta. The integral of sine 2 theta is negative 1/2 cos 2 theta, and the integral of cos squared theta is a half theta plus 1/4 sine 2 theta. Now you may notice that the half thetas could be added together to just make 1 theta, and even better, the minus 1/4 sine 2 theta could cancel with the plus 1/4 sine 2 theta. And the reason for that is because actually, as we know, and this is the reason why I've given us this question, sine squared plus cos squared is actually 1. So going back to our original expansion, okay, where we have a sine squared plus cos squared, we could just rewrite that as 1. And as we know, 2 sine theta cos 2 theta is going to be rewritten as sine 2 theta. So all we're actually doing is integrating 1 plus 2 sine theta. The integral of 1 is theta, and the integral of sine 2 theta is negative 1/2 cos 2 theta. What if we have P and Q as our coefficients, so generalizing that, and also having the K theta rather than just a single theta. So first thing to do is to expand the brackets. We are squaring, so we'll have a P squared sine squared K theta. We're timesing the two terms together in the brackets and doubling it, because there's two ways of making it. So 2pq sine k theta cos k theta, and then a q squared cos squared k theta on the end. Integrating those will require us again to simplify the middle term. So 2pq sine k theta cos k theta is the same as pq sine of 2k theta. And then we can go through and integrate each of those individually. I won't read it out, but that's our general expression. I'm not expecting anybody to learn that, but I'm just showing you that it's probably what you would expect to get, okay, for each of those individual terms. We'll just have a quick look at how we integrate things like sine 2 theta, sine theta, and sine 2 theta, cos theta, etc. So starting with sine 2 theta, sine theta. Sine 2 theta is again 2 sine theta cos theta. So if we replace sine 2 theta with that, we'll have two lots of sine which multiply together, giving us a sine squared plus the cos theta, and I've put the 2 outside the front as a multiplier. So integrating sine squared theta cos theta, that's one of those that you might do by the reverse chain rule. So if we started with sine cubed theta and differentiated it, we would get 3 sine squared theta multiplied by the differential of sine, which is cos, which is basically what we've got there, but without the 3. So the answer is actually 2/3 of sine cubed theta. So imagine differentiating that. The 3's would cancel out. You'd have a sine squared rather than sine cubed. You'd have the 2 that we need as a multiplier, but you'd also generate the cos theta as the differential of sine. So you'd be using the chain rule to do that. Okay, for the bottom left, sine 2 theta cos theta. Again, sine 2 theta is still 2 sine theta cos theta, but this time we're going to be squaring the cos rather than the sine. Same idea, it's the reverse chain rule, except this time we'd be starting with cos cubed theta, and the only difference really is that there's going to be a negative sign, because the differential of cos is negative sine. Therefore, if we start with negative 2/3 cos cubed theta, when you differentiate that, again the 3's cancel out, but when you differentiate the cos, you get negative sine, so the 2 negatives will then cancel out and give you the positive that we needed originally. Cos 2 theta sine theta. Now, don't forget that the expansion, or whatever you want to call it, for cos 2 theta, the identity for that is not as simple as it is for sine 2 theta. So for cos 2 theta sine theta, we really want to write it in terms of cos squared, on the basis that we can then use our ideas of reverse chain rule to integrate 2 cos squared theta sine theta, which is exactly what we've just integrated at the bottom left. Okay, so if we expand the brackets and rewrite it as 2 cos squared theta sine theta minus sine theta, and this time the 2 has to stay inside the integral because the sine theta itself on its own doesn't have one. So the integral of 2 cos squared theta sine theta, as we know, is minus 2/3 cos cubed theta, and the integral of negative sine is positive cos. So that's our answer. And then for the integral of cos 2 theta cos theta, we'd be starting with 1 minus 2 sine squared theta as our identity for cos 2 theta. Expanding the brackets gives us that, and this time we've generated a sine squared cos, which is what we had at the top left. So the integral of cos theta is sine theta, and the integral of negative 2 sine squared theta cos theta is the negative of our answer at the top left, negative 2/3 sine cubed theta. Generalizing it to what happens if we have more than one theta in the brackets. So sine 2k theta, that's going to be 2 lots of sine k theta cos k theta. So this time we're going to get 2 lots of sine squared k theta cos k theta. The answer is going to be very similar to what we got before, except we need to divide it by k. So 2/3k sine cubed k theta. And then if we've got cos 2k theta sine k theta, again, because it's a sine k theta on its own, we want to use the cos squared version of cos 2k theta, which is 2 cos squared k theta minus 1. Expand the brackets to get that, and then if you integrate 2 cos squared k theta sine k theta, that's the same as integrating 2 cos squared theta sine theta but dividing it by k. So that's the minus 2 over 3k cos cube k theta, and the integral of negative sine k theta is positive 1 over k cos k theta. What happens if we want to integrate cubes? So if you want to integrate sine cube theta, we could start off by splitting it into sine squared and sine, and then we can replace the sine squared with 1 minus cos squared, and now we're back in a very similar situation to on the previous slide, where we've got the sine theta term and a cos squared sine theta term. So that's that. If you integrate sine theta, you get negative cos theta. If you integrate negative cos squared theta sine theta, reverse chain rule, you get positive 1/3 of cos cube theta. And then for cos cubed 6 theta d theta, so it's still a cubed, it's cos, but we've now got 6 theta on the standard theta. We can start off by rewriting it as cos squared and cos for the 6 thetas. We can then rewrite that as 1 minus sine squared 6 theta for the cos squared 6 theta. Expand the brackets and then integrate each of those individually, which we've already been looking at. So the integral of cos 6 theta is 1/6 of sine 6 theta. The integral of sine squared 6 theta cos 6 theta, we need to divide it by 6 as well as the 3 from the reverse chain rule, because we're starting with the idea of sine cubed. So when we differentiate that, we're going to generate a 3. So we need a 3 on the denominator to cancel with that one, as well as the 6 from the fact that we've got 6 thetas. If we have cos to the 4 theta, I'm not going to go beyond 4 as an index, but if you start with cos to the 4 theta, d theta, and the same rules would apply for sine to the 4 theta, we can start off by rewriting it as the square of cos squared, and cos squared theta, when we integrated that earlier, we rewrote it as a half plus a half cos 2 theta. So imagine we're squaring that instead. Start by expanding the brackets. A half squared is a quarter. Times the terms together and double it. So we do get a quarter, but then we're doubling it to get a half of cos 2 theta. And then the square of half cos 2 theta is a quarter cos squared 2 theta. And we've integrated each of these individual terms earlier. So the integral of a quarter is a quarter theta. The integral of a half cos 2 theta is a quarter sine 2 theta. The integral of cos is positive sine, and we're dividing it by 2 because of the 2 theta. And then we've got a quarter of the integral of cos squared 2 theta. So remember that we get a half theta every time, but because it's cos squared 2 theta, we get a sine 4 theta. So we're doubling the 2 thetas there, and we're timesing it by 1/8, where 8 is 4 times the 2 theta, because we've got 1 over 4k before. Okay, finally, just for fun, and this isn't going to crop up in polar coordinates, but just to show you something that's a bit of light relief at the end. Imagine you were asked to integrate sine x over sine x plus cos x dx. Okay, you could try all sorts of things and they wouldn't necessarily work, but here's a clever way of doing it. So we define I1 as sine x over the integral of sine x plus cos x dx, which is what we've got there and what we want to work out. But then we also define I2 as the integral of cos x over sine x plus cos x dx. And you might think that doesn't make much difference. What is the point of doing that? Well, watch this. If we add them together, the denominators are the same, but on the numerator we're going to get sine x plus cos x. And I'm sure you can see that both the numerator and denominator are the same. So that's actually the same as integrating 1. And the integral of 1 dx is just x. So the integral, if we want to do I1 plus I2, the answer is just x, which isn't very helpful on its own. But the other thing we can do, if we subtract, so if we start with I2 minus I1, and we have to do it that way around for a reason you'll appreciate in a minute, we've got the cos x from the I2 minus the sine x, because we're doing I2 minus I1. And then you may notice that the numerator is actually the differential of the denominator. The differential of sine x is cos x, the differential of cos x is negative sine x. So the numerator is the differential of the denominator, and you should be aware, again from standard A-level maths, that if you have a differential of a function divided by the function and want to integrate it, that is log of the function. So this is log of the denominator, which is log of sine x plus cos x. And now we've essentially got simultaneous equations that we can solve to work out I1. So if we start with the x and subtract the log sine x plus cos x, that will give us 2 I1s. The I2s will cancel out. So 2 I1s is equal to x minus the log of sine x plus cos x. So the integral we want is simply a half of x minus log sine x plus cos x. I think that will do for us today. Okay, thank you very much.